Hello, I'm Vincent Royakers, and this is Lab 5, Magnet Drop Test. In this lab, we analyze the impact on velocity of dropping a magnet through a simulated solenoid. In this case, the solenoid was a roll of aluminum foil. The main properties used in this lab was Faraday's law, and this is because as we drop the magnet through the aluminum foil tube, the magnet induced a current, in this case a change in voltage in the coil, and this change in voltage causes a magnetic force. In this case it provides a magnetic force upward, and this creates a braking effect on the magnet, and this force acts counter to the force of gravity. And we can use this in conjunction with Newton's second law to help explain why there is a moment of constant velocity, which we'll see later. So going into the actual experiment. So in this case of this lab, I filmed myself dropping a magnet through the tube 5 times. I then put these clips into Tracker, and I analyzed the motion to get a time. And I found my average time to be 1.267 seconds for the magnet to fall all the way through the tube. So let's go to the code. So here's our code. So the first thing to notice is that we're reusing the magnet from the previous lab. So again, we're reusing our calculation for the magnetic field of a dipole. In this case, it's the same magnet, so it'll have the same magnetic moment, which again we're reusing. One thing that does change is the calculation for the change in flux in the foil, because as the magnet moves down, it's inducing a charge in the foil around it, which we'll go into detail later. But we can see that this calculation is used later on about here. So we can see, again, we're treating this, we're doing what is essentially an integral here. And each ring is a layer in the foil as we move down vertically. And in this case, we're using this change in flux to determine the current by dividing the foil's resistivity. And we can get this current, which is then used in the calculation to determine the magnetic force on this ring. And then we can add up all these magnetic forces of the ring to determine the magnetic force on the magnet overall. And it's this force that's counteracting the force of gravity. So if we run this program, we should see a counterclockwise current on the bottom, shown by the blue, and a constant velocity as the magnetic force is counteracting the gravitational force. The reason why we see a counterclockwise motion below the magnet is because of the magnet. As the magnet is going down, the magnetic flux below it is increasing, and then the foil, in an effort to repel it up, it has a counterclockwise induced current going around. So going into the conclusion. Going into conclusions, as we could see in the model, it fell slower than it did in real life. I guess one big thing that could account for that for me is that the measurements for the real life model were made using a cheap ruler that I got from Cora, so there might be human error to take into account for that. But otherwise, they're very close, and I feel like the computer model or the computation model is a reasonable approximation. So going into these questions, what if resistivity of the conductor was reduced to close to zero? So following Ohm's law, that voltage is equal to current times resistance. As the resistance gets lower and lower, this allows a larger and larger current to be allowed to equal to the voltage that we had. So I guess in the terms of dynamics of the magnet falling, it would take longer for it to fall because the current in the foil would be a lot stronger. And then if holes or slots were cut in the tube, this effectively just reduces the amount of rings, or I guess like the bounds of the integral. So this would allow the magnet to fall faster because there would be less current in the foil. Thanks for watching.